Hello everyone, I am Gargi Dash, and today I will be presenting on a topic that bridges research and real-world engineering challenges like fatigue and fracture mechanics in aluminum silicon-10 magnesium alloys produced through laser-powered bed fusion. Specifically, I'll discuss how a particular paper ties into my research and what we can learn about defect-driven fatigue behavior. Let's dive right in. Here are the contents that we would be discussing today: is a little introduction, the description of the problem, and analysis, and then the overview of the paper and how they have worked out different things. And I would also like to discuss the relevance of this paper to my research. Moving on. So why are we even talking about fatigue and fracture? The problem is simple. Things break, and from airplane wings to bike frames, fatigue failures happen, often with catastrophic consequences. Understanding the mechanics behind fractures helps us design better and safer materials. Now, additive manufacturing, especially laser-powered bed fusion, has revolutionized how we build these materials with the years. Moving on, but the fact that we should keep in mind is it's not without any challenges. While aluminum silicon-10 magnesium alloys are popular for lightweight aerospace and automotive parts, defects in these components significantly impact their fatigue performance. The performance of these materials under cyclic loading, particularly in fatigue-critical applications, remains a challenge till today. This is especially true for the aerospace industries, where safety and reliability are paramount. The mechanics of fracture and fatigue analysis provide a crucial lens to address these challenges, helping us design materials and processes that are robust and reliable. Moving on to the problem at hand. So, we know that LPBF introduces porosity, surface roughness, and residual stresses. These defects act as crack initiation sites, and components are often subjected to cyclic loads in the real-world applications, making it very critical to analyze fatigue. So we know that the problem lies in the inherent defects when in the process itself. So these defects act as stress concentrators and drastically reduce fatigue life. In addition, the unique microstructure resulting from LPBF process creates non-uniform mechanical properties, and understanding this interplay between the defects and fatigue is essential for enhancing the material's performance and extending its application scope. So here you can see in the image that I took from the paper, there are traces of gas porosity. There are lower keyhole pores and higher number of keyhole pores in these pictures. Moving on to the other challenges in LPBF-fabricated alloys, here is a graph which illustrates the difference in fatigue life between specimens with and without defects. So notice how the fatigue life drops significantly due to even small defects. That's because stress concentrations amplify crack growth, leading to earlier failure. This graph perfectly underscores the importance of minimizing defects during manufacturing to extend a component's lifespan. Moving on, let's talk a bit about the mechanics analysis of this process. So mechanically, fatigue is all about how a material responds to cyclic stress. So in the paper, they used Paris law to describe crack propagation rates. The equation for it's dA by dN equals C delta K to the power M dA by dN. So here the crack growth rate depends on the stress intensity factor delta K, When defects are present, they act as stress concentrators, increasing the delta K locally and accelerating the failure. In simpler terms, defects are like weak links in a chain, and they dictate where and how fast the fatigue is going to occur. So this graph demonstrates the relationship between crack growth rate, which is dA by dN, and the stress intensity factor range, delta K, highlighting higher growth rates due to residual stresses and process-induced defects. So here's the question I'm exploring. How can mechanics and fracture analysis address these issues in the alloy? This brings me to the paper I chose to study. First, let's look at some of the pictures used by the paper, where they show that in a conventionally produced cast alloy, the crack rather propagates very fast, but in an additively manufactured alloy, the crack propagates very slowly. So let's have an overview of the paper. Let me introduce the key study we'll focus on. So in this paper, the author investigated fatigue and short crack behavior in aluminum silicon 10 specimens produced by laser powder bed fusion. They focused on alternating bending loads to mimic real-world stresses. And the key takeaway here, they demonstrated how microstructural defects such as pores and inclusions significantly reduce fatigue life. The study is particularly relevant to my work because it connects material properties with performance, offering insights into optimizing additive manufacturing processes. Moving on to the methodology used here, the authors tested miniature samples or specimens of aluminum silicon 10 subjected to bending fatigue. They used scanning electron microscopy, or SEM, to identify defects and studied crack propagation using Paris law, a classic fracture mechanics model. They plotted fatigue lives and crack growth rates at various stress levels to assess how quickly cracks grew under different conditions. One critical aspect was correlating defect size and location to failure behavior. Here's an interesting part of their method. They also analyze short crack behavior, which behaves differently from long cracks. This makes sense if you think about it, like smaller cracks often grow faster initially due to stress concentration around defects. If you're feeling overwhelmed by science, here's a fun way to think about it. Cracks are like arguments in group projects. They start small, but they can escalate really quickly. Moving on to the key findings from the study, the results showed a direct relationship between defect size and fatigue performance. Larger defects reduced fatigue life by over 50%. Shorter cracks grew faster than predicted by standard models, and fatigue strength was significantly lower in specimens with high porosity. These results emphasize that defect control during manufacturing is crucial for ensuring reliable performance in critical applications. Here's an SEM graph used in the paper, which shows the eutectic silicon phase, the alpha aluminum cells, and also the micro cracks. So moving on to what the study contributed. So first of all, we had the fabrication of the alloy with the additive manufacturing technique of laser powder bed fusion. And they fabricated miniature specimens, and these were characterized by different techniques for microstructural defects. And these specimens were then subject to alternating bending fatigue testing. And then an assessment of the fatigue life was done. Then various failure mechanisms were identified, and later they developed analytical and simulation models and strategies to mitigate these defects and to enhance the fatigue life. Moving on to the relevance of this paper to my research. My research focuses on minimizing microstructural differences in aluminum silicon 7, which is rather similar to aluminum silicon 10 produced by LPBF. One key challenge is the trade-off between strength and fatigue performance. So the work that they presented in the paper aligns closely with my focus on defect reduction through optimized heat treatments. The findings validate the need to study crack initiation sites, especially in downskin regions where defects are more prevalent. So in a nutshell, we do face the similar challenges of porosity and residual stresses in the F357 alloy. And the methodology and models, they offer a blueprint for studying fatigue in future, and it aligns with my focus on improving the material performance for aerospace application. Here you can see in the micrograph, which was taken by me during my research, that there are various areas with pores, which shows that the F357 is in fact very similar to the aluminum silicon tin alloy. Moving on to the future directions for the research. Well, heat treatments can improve fatigue performance by reducing defect severity. For example, solution treatments coarsen silicon particles, mitigating stress concentrations. By applying concepts from the study, I aim to correlate defect size and distribution with fatigue performance, optimizing heat treatments to minimize failure risks. So the question is, what's next? So in my work, I plan to extend this research by studying defect formation mechanisms during LPBF, developing fatigue models that account for unique defect characteristics, and performing experimental fatigue tests to validate these models. Hopefully, I'll have fewer arguments, cracks, to deal with along the way. So here is some of a test that we did recently. So to rather homogenize the microstructure, which we believed could mitigate the defects and remove or lower the porosity of the alloy, we did a T6 heat treatment, and we did a solution treatment at the high temperature of 530 degrees Celsius for 1 hour, and followed by an aging at the rather lower temperature of around 160 degrees Celsius for 6 hours. And we see a rather homogeneous microstructure in the bulk and in the downskin. Moving on to the summary. So to wrap up, the study demonstrates how defects compromise fatigue life in aluminum silicon tin. Their work provides a strong foundation for defect-driven fatigue analysis, which is central to my research. Understanding these mechanisms help us build stronger, safer materials. And as engineers, isn't that what we are all striving for? And as a final remark, I think fatigue analysis bridges the gap between LPBF's promise and its challenges, and understanding the short crack growth ensures safer application in critical industries. And research like this underpins achievements in additive manufacturing. These are the references. Thank you for your attention. Goodbye.